China establishes world's first 3-satellite constellation in the Earth-Moon region. Date of achievement, April 16, 2025. China has achieved a groundbreaking milestone in space exploration by successfully establishing the world's first 3-satellite constellation in the Earth-Moon region, specifically situated in the Distant Retrograde Orbit DRO. This significant development is expected to enhance future space exploration capabilities, including manned missions beyond Earth. The announcement was made by the Chinese Academy of Sciences (CAS) and has been widely reported by various media outlets including Global Times, Anadolu Agency, and Xinhua. Overview of the constellation. The 3-satellite constellation comprises DRO-A, DRO-B, DRO-L. DRO-A and DRO-B were launched on March 13, 2024, while DRO-L had been launched earlier on February 3, 2024. Initial deployment faced a challenge due to an anomaly during the launch of DRO-A and DRO-B. But corrective maneuvers allowed these satellites to enter their designated orbits by July 15, 2024. Key features and innovations. 1. Low-energy insertion. One of the most notable achievements was the satellite's entry into the DRO using only 1/5 of the fuel typically required. This innovation represents the world's first successful low-energy insertion into a DRO, significantly reducing costs for accessing cislunar space. 2. Inter-satellite communication. The constellation successfully established a K-band microwave communication link over a distance of 1.17 million kilometers. This development marks a significant technological advancement for large-scale constellation operations in cislunar space. 3. Orbit determination system. A pioneering satellite-to-satellite tracking system was validated, achieving orbit determination accuracy that would usually require 2 days of ground-based tracking, but was accomplished within just 3 hours of inter-satellite data. Strategic importance of DRO. The distant retrograde orbit is a unique orbital path that offers several advantages. Stability. The DRO provides a stable platform with minimal fuel requirements for spacecraft operations, making it an ideal hub for connecting Earth, the Moon, and beyond. Applications. The establishment of this constellation supports a range of applications including lunar resource exploitation, long-term human habitation in space, and interplanetary activities. The DRO is characterized by its ability to support operations and facilitate research, making it an essential element for future missions and technological developments. Timeline of developments. 1. 2017. Initial research on the Earth-Moon region's astrodynamics began. 2. February 2022. A pilot project was initiated for the development and launch of 3 satellites to form a constellation. 3. February 3, 2024, the DRO-L satellite was launched into a sun-synchronous orbit. 4. March 13, 2024, DRO-A and DRO-B were launched but initially failed to reach their intended orbit due to a launch anomaly. 5. July 15, 2024, after corrective maneuvers both DRO-A and DRO-B successfully entered their designated orbits. 6. August 2024. The constellation became operational with established inter-satellite communication links. Scientific and technological implications. The establishment of the satellite constellation paves the way for numerous scientific explorations. Astrophysical research. The satellites are expected to support research in astrophysics, including gamma-ray burst detection, quantum mechanics, and atomic physics. Researchers plan to conduct fundamental studies in these fields, leveraging the stable environment of the DRO. The program will also facilitate future lunar exploration missions, providing vital space-based measurement and navigation services. Challenges and innovations. The successful deployment of the constellation was not without challenges. The launch of DRO-A and DRO-B encountered significant obstacles, requiring a life-or-death rescue operation to correct their trajectories. The satellite team executed multiple emergency maneuvers under pressure, successfully positioning the satellites in orbit. The achievements of this mission underscore China's advancements in deep space fault recovery, autonomous navigation technologies, and cost-effective exploration strategies. The innovative approaches taken during the mission highlight the flexibility and adaptability of the satellite team in complex missions. Conclusion: China's establishment of the first 3 satellite constellation in the Earth-Moon region is a landmark achievement in space technology. This initiative not only enhances China's capabilities in space exploration but also sets the stage for future research and potential commercial activities in cislunar space. With its strategic location and technological advancements, the DRO constellation is poised to play a crucial role in advancing humanity's exploration of space. As China continues to explore and utilize the Earth-Moon region, the insights and technologies developed through this mission will likely influence future interplanetary endeavors and the ongoing quest for sustainable exploration of the solar system. Counterintuitive information identified. 1. Fuel efficiency and cost reduction. Typically, one would expect that advanced technologies and the establishment of a new satellite constellation would lead to increases in operational costs due to the complexity and novelty of the systems involved. However, the development of the Distant Retrograde Orbit DRO constellation demonstrates the opposite. The satellites achieved their orbit using only 1/5 of the fuel normally required for such missions, which is a significant cost-saving measure. This counterintuitive outcome suggests that innovative engineering solutions can dramatically lower the costs of space exploration. 2. Orbit stability versus complexity. One might assume that more complex orbital paths and satellite maneuvers would lead to less stability and more challenges in satellite operations. However, the DRO is characterized as a highly stable orbit that requires minimal fuel for spacecraft to enter and maintain. This stability makes it a natural hub for space operations, contradicting the expectation that stability would be sacrificed for operational flexibility. 3. Inter-satellite communication over ground stations. It's commonly believed that ground-based tracking and communication systems are the backbone of satellite operations, especially for navigation and data transmission. The success of the satellite-to-satellite tracking system, which achieved orbit determination accuracy in hours instead of days, challenges this notion. This innovative approach reduces reliance on ground stations and suggests that space-based systems can be more efficient for tracking and data management. For scientific research opportunities in a remote orbit, one might think that being farther from Earth would limit research capabilities and scientific opportunities. However, the DRO's unique environment is being leveraged for fundamental studies in quantum mechanics and atomic physics, which is unexpected given the distance from traditional research facilities and the challenges of operating in such remote locations. 5. Manned missions feasibility. Traditionally, deep space missions have been viewed as highly complex and resource-intensive endeavors requiring significant human and technological investment. The establishment of the DRO constellation, viewed as a strategic move that facilitates future manned missions, suggests that such missions may become more feasible and less resource-dependent in the future, contrary to the inclination to view them as prohibitively expensive and complex. 6. Ecosystem for lunar resource exploitation. The narrative around space exploration often emphasizes the monumental costs and risks of lunar resource exploitation. However, the DRO constellation's development could indicate that the exploitation of lunar resources may be achieved more easily and affordably than previously anticipated, challenging the perception of lunar missions as solely high-stakes endeavors. 7. Perception of international competition. The establishment of a pioneering satellite constellation in cislunar space might typically be viewed as a competitive move that heightens tensions in international space endeavors. However, the advancements made by China in this area could lead to increased cooperation and shared technological benefits globally, which counters the narrative of space exploration as a zero-sum game. 8. Role of satellite constellations in future infrastructure. While satellite constellations are often associated with telecommunications and Earth observation, the successful establishment of a constellation in the Earth-Moon region suggests a broader role for these systems in supporting future infrastructure in space. including navigation and communication for lunar and interplanetary missions. This challenges the existing frameworks that classify satellite functions strictly by their immediate applications on Earth. 9. Public perception of space exploration success. It may be assumed that achievements in space exploration are universally met with enthusiasm and optimism. However, the intricate details of setbacks such as the launch anomaly that delayed the deployment of DRO-A and DRO-B highlight the challenges and complexities involved in such missions, prompting a more nuanced understanding of success that encompasses both triumphs and tribulations. By recognizing these counterintuitive elements, one gains a deeper understanding of the implications and potential transformations in the field of space exploration brought about by China's establishment of the world's first 3-satellite constellation in the Earth-Moon region. China's establishment of the world's first 3-satellite constellation in the Earth-Moon region, specifically on the Distant Retrograde Orbit DRO, marks a pivotal advancement in space exploration and technology. While the main achievements and milestones of this project have been highlighted in various reports, several aspects may be overlooked by the general public that are both significant and indicative of future trends in space exploration. 1. Low-energy insertion technology. The ability to achieve low-energy insertion into the DRO using only 1/5 of the fuel typically required is a groundbreaking achievement. Most reports mention this innovation, but its broader implications are often glossed over. Significance. This technology radically decreases the costs associated with launching and maintaining spacecraft in cislunar space. Historically, fuel consumption has been one of the largest barriers to deep space exploration. So this breakthrough could lead to a paradigm shift in how missions to the Moon and beyond are planned. The reduced fuel requirements mean that missions could carry more scientific instruments or extend their operational lifetimes, increasing the scientific return from each mission. Furthermore, this could facilitate more frequent launches and the establishment of a sustained human presence in space, ultimately contributing to the long-term goal of interplanetary exploration. 2. Inter-satellite communication innovations. The establishment of a K-band microwave communication link over a distance of 1.17 million kilometers is reported as a significant technical accomplishment. However, the specific benefits of this technology for future space missions are often understated. Significance. This communication system enhances the operational capabilities of satellite constellations in cislunar space, allowing for real-time data sharing and coordination among satellites. Such systems are essential for complex missions involving multiple spacecraft, as they can facilitate quicker decision-making and enhance the accuracy of navigation and timing services. The implications extend beyond this constellation. Similar communication systems could be applied to future interplanetary missions, improving our ability to explore and utilize resources across the solar system. 3. Orbit determination system. The development of a new satellite-to-satellite orbit determination system, which can provide accuracy equivalent to traditional ground-based tracking in a fraction of the time, is another crucial aspect that may not receive sufficient attention. Significance. This innovation represents a shift in how spacecraft can be monitored and managed. Traditionally, spacecraft operations relied heavily on ground stations, which can be limited by geographical and technological constraints. By utilizing satellite-based tracking systems, missions can achieve greater autonomy and flexibility, reducing the dependency on ground infrastructure. This could be particularly beneficial for deep space missions where communication delays with Earth are significant. The ability to determine orbits quickly and accurately can improve mission planning and execution, ultimately enhancing the safety and success rates of complex space operations. 4. Strategic importance of the distant retrograde orbit. While many reports touch upon the DRO's stability and fuel efficiency, the strategic implications of utilizing such an orbit for future space endeavors are often overlooked. Significance. The DRO serves as a natural hub for connecting Earth, the Moon, and beyond, enabling a variety of applications such as lunar resource exploitation and long-term human habitation. The strategic positioning of satellites in the DRO could streamline operations for lunar missions and support the establishment of a sustainable human presence on the Moon. This region's unique characteristics could also support scientific research in various fields, including astrophysics and planetary science, making it an ideal location for a new generation of space observatories and research facilities. 5. Interdisciplinary research opportunities. The planned studies in quantum mechanics and atomic physics utilizing the stable environment of the DRO showcase an unexpected aspect of the constellation's purpose that may not be emphasized. Significance. These research opportunities could lead to advancements in various scientific fields, potentially resulting in new technologies and methodologies. The ability to conduct experiments in a low-gravity stable environment opens avenues for research that are not feasible on Earth. This could enhance our understanding of fundamental physical processes and contribute to the development of new materials, advanced propulsion systems, and other applications that benefit both space exploration and terrestrial technologies. 6. Global competition and collaboration in space. While the technological advancements are significant, the geopolitical implications of China's achievements in space exploration may be underappreciated. Significance. As nations increasingly recognize the strategic importance of space, China's establishment of a 3-satellite constellation in the Earth-Moon region signifies its growing capabilities and ambitions in space. This development could spur increased competition among global powers, leading to a renewed focus on national space programs and collaborations. The actions taken by China may encourage other nations to invest in their own space technologies and infrastructures, fostering an environment of both collaboration and competition that will shape the future of space exploration. Conclusion. China's establishment of the first 3-satellite constellation in the Earth-Moon region is not merely a technological achievement, it has far-reaching implications for the future of space exploration, international cooperation, and scientific research. The innovations in low-energy insertion, inter-satellite communication, and orbit determination systems, alongside the strategic utilization of the DRO, highlight a new era of possibilities in cislunar space. As the world watches these advancements, it is crucial to recognize the broader context and potential consequences, ensuring that we are prepared to navigate the complexities of our expanding presence in space. Here are the 4 most valuable points in the content regarding China's establishment of the world's first 3-satellite constellation in the Earth-Moon region of space for in-depth analysis and discussion. 1. Technological innovations in space exploration. The establishment of the 3-satellite constellation DRO-A, DRO-B, and DRO-L represents a significant technological advancement in space exploration. Key innovations include low-energy insertion. The satellites achieved entry into the Distant Retrograde Orbit DRO using only 1/5 of the fuel typically required. This breakthrough not only minimizes operational costs but also opens up new avenues for large-scale space exploration, making it more feasible for future missions to access cislunar space. Inter-satellite communication. The successful establishment of a K-band microwave measurement and communication link over a distance of 1.17 million kilometers is a monumental achievement. This capability enhances the operational integrity of satellite constellations and facilitates data transmission essential for scientific research and navigation. Orbit determination system. The validation of a satellite-to-satellite tracking system that can determine orbits with precision equivalent to 2 days of ground-based tracking in just 3 hours of inter-satellite data is groundbreaking. This innovation greatly reduces the costs and time associated with space navigation and tracking, making future missions more efficient. These technological milestones not only enhance China's capabilities in space but also position the country as a leader in space exploration technologies, potentially influencing global space policies and collaborations. 2. Strategic importance of the Distant Retrograde Orbit DRO. The DRO is highlighted as an optimal location for establishing a stable platform for satellite operations. Its characteristics provide several strategic advantages. Stable orbital platform. The DRO stability allows for minimal fuel requirements for spacecraft operations, making it an ideal hub for future exploration missions. This natural advantage is crucial for long-term human habitation and resource utilization beyond Earth. Gateway to deep space exploration. The constellation's location in the DRO serves as a strategic gateway for connecting Earth, the Moon, and beyond. This positioning is vital for facilitating interplanetary activities and establishing communication links with lunar missions. Research opportunities. The DRO's unique environment offers researchers the ability to conduct fundamental studies in areas such as quantum mechanics and atomic physics, leveraging the stable conditions for advanced scientific experiments. This can lead to significant breakthroughs in various scientific fields. The strategic significance of the DRO emphasizes its potential role as a linchpin in future space exploration efforts, which can reshape humanity's approach to interplanetary travel and resource utilization. 3. Implications for future lunar exploration and human habitation. The successful establishment of the satellite constellation sets the stage for various future missions, particularly in lunar exploration. Support for lunar missions. The constellation will provide essential space-based measurement and navigation services for upcoming lunar exploration missions. This includes high-precision timing signals for lunar surface facilities and autonomous navigation for orbiters, crucial for the success of manned missions. Resource utilization. The ability to explore and potentially exploit lunar resources becomes more viable with the support of the satellite constellation. This could lead to sustainable operations on the Moon, assisting in the development of infrastructure necessary for long-term human habitation. Interplanetary exploration. The advancements in navigation and communication technologies fostered by this project will likely facilitate further exploration of Mars and other celestial bodies, expanding the frontiers of human presence in space. These implications highlight the broader impact of this technological achievement on humanity's aspirations in space, particularly regarding sustainable exploration and habitation beyond Earth. 4. Global space dynamics and international competition. China's achievement in establishing the first 3 satellite constellation in the Earth-Moon region marks a pivotal moment in the global space race, raising several critical points for discussion. Technological leadership. By pioneering this constellation, China positions itself as a leader in space technology, potentially reshaping global space dynamics. Other nations may feel compelled to accelerate their own exploration initiatives or collaborate with China to leverage its advancements. Strategic partnerships and alliances. This development may lead to new partnerships in the international space community as other countries seek to enhance their capabilities through collaboration. China's technological advancements could be a catalyst for forming new coalitions or agreements focused on space exploration. Geopolitical implications. The establishment of a strong presence in the Earth-Moon region raises geopolitical considerations such as the militarization of space or competition for lunar resources. The strategic importance of cislunar space could lead to tensions or conflicts over territory and resource rights. These factors underscore the significance of China's achievement not just in terms of technological progress but also in its potential to influence global governance and cooperation in space exploration. In summary, the establishment of China's 3-satellite constellation in the Earth-Moon region represents a landmark achievement with profound implications for technology, strategic positioning in space, future exploration missions, and international dynamics in space exploration. Each of these points offers rich avenues for in-depth analysis and discussion. 1. The Apollo Program 1961–1972. The United States Apollo program was a series of missions aimed at landing humans on the Moon and bringing them safely back to Earth. Apollo 11, which took place in July 1969, marked the first successful manned mission to the lunar surface, with astronauts Neil Armstrong and Buzz Aldrin walking on the Moon while Michael Collins orbited above. The program culminated in 6 successful lunar landings and played a pivotal role in advancing space exploration technologies, international prestige in space science, and scientific knowledge of the Moon. The program's legacy continues to inspire space exploration efforts globally. 2. The Soviet Luna Program 1959 to 1976. The Soviet Union's Luna program was a series of robotic spacecraft missions aimed at exploring the Moon. Notably, Luna 2 became the first human-made object to impact the Moon in 1959, and Luna 9 achieved the first successful soft landing on the Moon in 1966, sending back the first images from the lunar surface. The program contributed significantly to lunar science, providing data about the Moon's surface and environment, and set the stage for future manned missions. 3. The European Space Agency's ESA Smart 1 mission 2003 to 2006. ESA Smart 1 was a technology demonstration mission that aimed to test new propulsion systems and conduct scientific observations of the Moon. Launched in September 2003, it utilized ion propulsion to travel to the Moon, marking the first time this technology was used in a lunar mission. Smart 1 successfully entered lunar orbit in February 2004 and conducted various scientific observations, including mapping the Moon's surface and studying its mineral composition. The mission's innovative use of technology and its scientific contributions have influenced subsequent lunar exploration missions. Future outlook: predictions for China's 3-satellite constellation in the Earth-Moon region. China's establishment of the world's first 3-satellite constellation in the Earth-Moon region marks a significant milestone in space exploration, particularly in the Distant Retrograde Orbit (DRO). This groundbreaking achievement is expected to have profound implications for future space endeavors, including lunar exploration, deep space missions, and advancements in space-based technologies. 1. Enhanced lunar exploration and resource utilization. The stable environment of the DRO will serve as a strategic platform for future lunar missions. The constellation is poised to facilitate a series of lunar exploration initiatives, including lunar base development. The DRO's low fuel requirements make it an ideal site for establishing a lunar base. This base could serve as a staging point for manned missions to the Moon and beyond, supporting long-term human habitation and resource extraction. Resource exploitation. China's lunar exploration strategy is likely to focus on identifying and utilizing resources on the Moon, such as water ice and rare minerals. The constellation's capabilities will enhance remote sensing and mapping of lunar resources, paving the way for sustainable exploitation. 2. Deep space missions and interplanetary exploration. With the groundwork laid by the 3-satellite constellation, China is expected to expand its ambitions beyond the Moon, Mars, and beyond. Following successful lunar missions, China may leverage its DRO constellation to support interplanetary missions, including Mars exploration. The data and navigation services provided by the satellites will enable more complex missions to distant planets. Asteroid mining. As interest in asteroid mining grows, the DRO constellation could provide essential support for missions aimed at exploring and utilizing asteroids, offering new resources for Earth and space industries. 3. Advanced scientific research. The constellation's unique positioning allows for a variety of scientific experiments that could lead to breakthroughs in multiple fields. Fundamental physics. The stable environment of the DRO will facilitate experiments in quantum mechanics and atomic physics, potentially leading to new discoveries that could revolutionize our understanding of the universe. Astrophysics studies. The satellites can contribute to astrophysical research, such as gamma-ray burst detection and cosmic background radiation studies, enhancing our knowledge of cosmic phenomena. 4. Technological innovations and economic implications. The successful integration of advanced technologies in the DRO constellation will likely spur further innovations impacting both the space industry and broader technology sectors. Satellite communication. The inter-satellite communication capabilities established in the DRO will enhance the development of global satellite networks, improving communication services and data transmission for various applications, including Earth observation and disaster management. Cost-effective space missions. The low-energy insertion techniques and satellite-to-satellite tracking systems developed for this constellation will reduce the costs associated with space missions. This economic efficiency may encourage more countries and private enterprises to engage in space exploration. 5. International collaboration and competition. China's advancements in the Earth-Moon region may reshape the global landscape of space exploration. Collaborative efforts, as cislunar space becomes increasingly significant. China may seek partnerships with other nations to share knowledge, resources, and technology, fostering international collaboration in space exploration. Geopolitical dynamics. Conversely, China's growing capabilities could intensify competition in space, particularly with nations like the United States and members of the European Space Agency. This competition may drive further investments in space technology and exploration. 6. Commercial opportunities. The establishment of a stable orbital platform in the DRO will create new commercial opportunities. Space tourism. As the technology matures, the potential for lunar tourism may become viable, attracting commercial interest from private space companies and investors. Commercial launch services. The advances in low-cost space access will likely lead to the growth of commercial launch services focusing on cislunar missions, providing opportunities for private enterprises to participate in the burgeoning space economy. Conclusion. China's pioneering efforts in establishing a 3-satellite constellation in the Earth-Moon region herald a new era in space exploration. The implications of this achievement extend beyond lunar missions, potentially transforming our approach to deep space exploration, scientific research, and commercial opportunities in the cosmos. As China continues to innovate and expand its capabilities, the global landscape of space exploration will evolve, presenting both challenges and opportunities for collaboration and competition. The next decade will be critical in determining how these developments shape humanity's presence in space.